can tell it's my notes just because the font's different. I just typed it up last. There are two types of differential equations in this course. Well, I guess there's two. I could argue three. Y dx equals x times y. We call that a separable differential equation because you get the x to one side, you get the y to one side. You take the antiderivative of both sides and you're off to the races. You could argue that the acceleration, taking the antiderivative, getting velocity, taking the antiderivative, getting position is another kind of differential equation, but I argue that they're both separable, so they're kind of the same thing. But the one that we're going to talk about today is dy dt equals ky. These are called linear first order differential equations. Why linear? Because the right-hand side of the equation looks like a line. Y, except it's not y equals, it's mx plus b, just the x is the y. It's going to look like sort of like a little equation of a line on the right-hand side. So they're called linear because it looks like a line on the right-hand side of the equation. It's said to be first order because it's the first derivative. Okay? So you can get very technical in language. Linear first order differential equations. Yes, they get technical. Yes, they get complicated, but not until third year university. Then you'll do 2 or 3 classes. If you're in math, you'll do 2 classes in differential equations. If you do physics degree, you'll do 2 courses in differential equations at the 300 level. And if you're in engineering, you'll just do differential equations all the time and plus on Friday. Because most of what engineering is about solving equations that have to do with stuff that's changing. Right? Okay. No, they're fun. I like them. But they're technical and they can be really challenging. These ones are not. Okay, I'm telling you that right now. They're not. Okay? What we're saying is the function is growing at a rate that is proportional to its previous quantity. So one of the best ways of doing that is if we talk about a population of sheep and we count them and then 10 days later there's more and it always seems to be growing that's proportional to the amount that we had before. Or falling according to the amount that we had before. So all functions that have a starting equation of dp dt equals k times p is p equals p0 e to the kt. Does anybody recognize that? Poke it. You didn't get those? Ooh. Evidence. So what I would like to do is let's take the derivative of poke it. Let's take the derivative of poke it. So the derivative of the left-hand side is, you could call it p prime or dp dt. So dp dt equals, okay, so the derivative of poke it is, copy the constant down, right? And then what's the derivative of e to the kt? Times the derivative of kt. What's the derivative of kt? Yeah. Now take a look at what happens. Try that again. I'm going to highlight what we started with. Starting amount. P0 is just the starting quantity. Mr. App, that's right here. So you could take out the stuff in this yellow box and replace it with just P. So dp dt equals P times K. Now, most of the time, I don't give you the starting equation and ask you to write it in its derivative form. We start with the derivative form, and I ask you to write it in its original function shape. So all I'm asking you to do is when you see this, you go backwards and write it like that. So the question I give you right away, example 1, find the solution to the differential equation dp dt equals 0.03p. So you can identify one thing right away. It fits the form of poke it, and it tells you something. Tells you k, yeah, k is 0.03. And then it says P of 0 is 200. So what am I asking you to do now? Solve P0. So 200 equals P0 e to the 0.03 times 0. Dun dun dun. Lo and behold, P0 is 200. So is this anything different than what we did in Math 12? Yeah, the notation is a little bit different, but the ideas of what does the E stand for, it's continuous growth, what's K, the growth rate, blah, 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 blah. It's the same stuff. Okay, look at example 2. So I don't give it to you in a differential equation form. A population doubles every 5 hours. What is the value of K? Did I tell you what you started with? Did I tell you K? No. Did I tell you what you finished with? No. Did I tell you how long? Yeah. So what population are we, how much are we going to start with? Anything. Well, okay, anything. So I'm going to start with 1 and you're going to finish with 2. E to the K, we don't know what K is. What's T? 5. 5 hours, yeah. So you get 2 equals E to the 5K. Now it's really Math 12. On it, yeah. ln2 equals 5K ln E. Whatever that is. I don't know, you got a number for me? So you could say this population has a growth rate of 14% per hour. Compounds continuously, 14% per hour. Okay? Hard. You might, if you were in a math class at university, you wouldn't see 2 equals 1. You would say, you'd see P0 and 2P0. But, woo, 2P0 divided by P. Like, it's really the same. Okay, flip the page. So, I got creative last night. Do you guys know what capacitors are? Okay, what's a capacitor? A flux capacitor. Those only work at 88 miles per hour. No. Capacitors are a really capacitors are a way of delivering large amounts of voltage in a very short period of time. So if you need a lot of voltage to do something quickly, you use a capacitor. But if you need a large amount of voltage over a long period of time, you don't want to use a capacitor. The most common capacitor you guys would know about is the ones in the camera flash. You'll actually hear it charge in the old school cameras. You'll hear it, and it's charging capacitor. What? Don't big safety thing, like don't play with charged capacitors. You can hurt yourself quite badly. Well, think about it. They store voltage. They store, exactly. They store voltage, and then they let it go quite fast. Pardon me? They might have capacitors in them. I don't know, but capacitors like a really powerful capacitor is about as big as my coffee mug, and you can kill somebody with that one. Like when it's fully charged. Deadly. Don't. Well, where are you going to see them? Where are you going to see them? You know what? I haven't seen. I've only seen them in engineering labs when we were doing stuff on capacitors. But I just know that they're not safe. Lucas is going to tell us.
They made these little tiny ones in shotgun shells that have little prongs on them.
Yeah, I don't know. Called a tape? Is that no?
No, it's like you shoot an electrified shell at something. It has like latches onto them and shots. It was like non-lethal, but like you're shooting.
It's like a taser, but not a taser.
You're like shooting a taser out of a shotgun.
Did anybody see a problem with?
There's a gun now. There's like a rifle now that you can shoot.
They might. Yeah, sorry. A taser, yeah, it probably operates on the same. Okay. There's a rifle that.
You can shoot. You can use change settings on it, and if you shoot it, the bullets explode at whatever percent you want. Like a grenade, and they explode at the same capacity. So you can shoot.
Okay, cool, but why?
Because if there's like a window or something or a door, and like you're.
Oh, I saw that on. What show was that on? It was something on the Discovery Channel. What show was it on though? I saw it on a. I was gonna say it's time to go down to the. I was gonna say. Okay. Anyways, so suppose the electricity is draining from a capacitor at a rate that is proportional to the voltage across its terminals. V is measured in volts, T is in seconds. So dV dt equals -1/40V. So create a formula. V equals V0 E. Yeah, it's vocate now. V equals V0 E to the -1/40T. Woohoo, A is done. B, how long does the voltage take to drop to 10% of its original value? So if you start with 100%, do I want to do this like a university prof, or do I want to do this like a high school teacher? High school teacher would do this. A university prof you would probably see this. You get the same answer because the next step is exactly the same. You get 0.10 equals e to the -1/40t. Here you get 0.10 v0 over v0. You get the same thing really fast. ln and then you divide or you multiply by the reciprocal. And you're finished. Are we good? Yeah. I was going to do a whole bunch of stuff on Newton's law of cooling, but when I looked on the AP exam, they didn't even talk about it, which is too bad because I was going to show you how coroners use liver temperature for time of death. It's actually a differential equation that you use. Now, coroners don't solve a differential equation. They just look it up in a chart. But I was going to show you where those numbers come from. But whatever. No. Do you guys want to? Okay, so I'm going to do this. Okay, have I seen a real live autopsy? Spencer, no, I haven't. Really? Okay, so you want to see this for 10 seconds? Is that what you're saying? Or you don't care? Okay. Soup. Okay, so I start with an obvious one. Hey, folks, you asked. Soup left in a cup cools to the temperature of the surrounding air. A hot silver ingot immersed in water cools to the temperature of the surrounding water. Makes sense, right? You take something hot and you take it out and you put it somewhere. It's going to cool to the temperature of the medium that it's sitting in. Okay? How do you make something cool faster? You reduce the air temperature. Or, how do you make something cool faster? Don't put it in a container that retains heat and then ask it to cool down to air temperature, which is what coffee cups do. The whole idea of what a coffee cup is supposed to do is keep it cool on the outside and hot on the inside. Exactly. Yeah. You want to decrease the surface area of the container, but you also want to make sure that the material that the container is being made out of is not a good conductor of heat. So if you... Yeah. So if you increase the surface area, it'll cool down much faster. And also, if you place it on something that conducts heat really well, which is what cooling is, right? Cooling is the absence of heat. So if you want to cool something down, you put it on something that's a good conductor. Well, duh. It's funny, you watch those TV shows where you go, the super defroster. Well, duh, you're putting it on a piece of metal. Metal is a wonderful conductor of heat. Yeah. I mean, you take a cup of coffee and you pour it on Mom's cookie tray, and measure its thermometer, and you put a thermometer in the coffee mug. Of course, the coffee mug's going to, because the surface area, and the coffee mug is designed as an insulator. Ceramics are good insulators. Because the heat of the spoon, the metal in the spoon is conducting the heat. It's almost, anyways, you have to kind of think about that. So, the example that I was going to, I get excited here. Sorry. The temperature of a cooling body always is according to this formula. T equals T A E to the negative K A E to the negative. I don't know, you got a little bit of room. Well, the whole, well, we screwed up. So the formula, this is the solution to the differential equation we're going to use right now. So please discover the body of Mr. F. I always love to do this question because it's scary and upsetting at the same time. Please call the coroner. Well, I have a chapter test that it's the whodunit. I have a list of suspects, and you always suspect the quiet one. Did you? Ew. Yeah, I know. It's like, ew. Yeah, and my response is the same. Ew. No. Okay. Please call the coroner who arrives at noon. Well, because she immediately takes the temperature of the body, because I'm not alive anymore. Why wouldn't she be? And finds it to be 94.6 degrees Fahrenheit. She waits 1 hour and takes the temperature again and finds it to be 93.4 degrees Fahrenheit. She also notes the temperature of the room is 70 degrees Fahrenheit. When was the murder committed? So what we need to know is, on average, the human body's temperature is 98.6 degrees. What? Yeah. It's a factor. It is a factor for measuring time of death, is body liver temperature. No, we could do it with Celsius if you'd like. So the first thing we need to know is, at time T equals little 0, the body temperature is 98.6 degrees. We also need to know the room temperature. big C is 7 degrees. Okay. The time t equals 0, t is 98.6.
Do we even know where we're supposed to put these? Like,
Yeah, no, I'll explain. I'll show you where it all comes from. And then at time t equals x, so when they find the body, it's 94.6. And at time t equals x plus 1, the body's temperature is 93.4. So the question tells you all of this information. So the first step in the process is to take all of this information and put it into the formula. So big C is 70, big T is 98.6, little t is 0. And that tells you some stuff. 98.6 equals a e to the negative k times 0 plus 70. What does this step tell you? No. It tells you little a. Because e to the negative k times 0 is 1. So it just tells you a is 28.6. Okay? So now we know that. And then we go back to the beginning and we take this information and we put it in the formula. So we get 94.6 equals 28.6 e to the negative kx plus 70. Tell me something we can do with that. Good. Isolate the negative kx. So move to 70 and you get 24.6 equals 28.6 e to the negative kx. Now what? ln 24.6 equals negative kx l. Whoops. No, wait. Before we ln. Yeah. 24.6 divided by 28.6 equals now ln. Can you do anything out with that? The short answer is no. Other than you could work the left-hand side out as a decimal. Would you like to do that or just leave it like that? You just leave it like that. Okay, so you start again. So with the other piece of information, 93.4 equals 28.6 e to the negative kx plus 1. Yeah, exactly. You know exactly where we're going. So move to 70, 23.4 equals 28.6 e to the negative kx plus 1. Divide. Sure, that's probably not a bad idea. Yeah. Yeah, give me 2 minutes and they can do that. Now, Curtis is exactly right. Hey, Mr. App, you know what negative kx is. So you take out negative kx and you put that right there. You can solve for k, and then once you know k, you can find x. And then you know that I've been dead for an hour and 30 minutes. So if it's noon when you find the body, go back an hour and 30 minutes and it's 10:30. TOD is 10:30. Ish. It's ish. It's not exact. It's an ish answer, right? Because air temperature doesn't stay at 70 degrees Fahrenheit all the time. That's just me making it up. And you're assuming that I'm normal. 98.6 degrees is my body temperature. So you're making some assumptions. Air temperature is staying constant, and my body temperature is about 98.6 degrees Fahrenheit.
So like, say for example, you're a runway and this guy just going through
Yeah.
body temperature and stuff.
Right.
That's the 10 o'clock.
Yes. Yeah. Exactly. So that's the whole. That's why I say it's about, right? And then there was a whole CSI episode about how they can monkey with the TO time of death, or at least the estimate was they turned on the air conditioning, so the air temperature was much lower, and then the air conditioning shut off, so the person's body temperature decreased really rapidly because the air conditioning was on, so it overestimated the time of death. It said it was 5 hours before, and it was only 3 hours. So you can play with. So it's always just a rough estimate. It's another measure that a coroner uses to determine time of death. When does rigor mortis set in, and when does it leave? And that's biology. I can't answer that question.
So what is our answer? Our answer is 0.05, and that's the
So K is 0.05. So what K is actually how fast how good my body is a conductor of heat. That's what K is.
Oh, so we just put that back in.
And so you take, what'd you say what K was?
0.05.
0.05. So what you do is now you put that number right there, and you can find X. So you're going to go ln 24.6 divided by 28.6. Get an answer divided by negative 0.05, and you're going to get the number of hours since death, or since the body was found. So the body so X might be 2. So 2 hours before I died. So if you know the time, if it's noon, go back 2 hours, 10 a.m. Cool. It's a neat application. The AP exam doesn't go this far, which is exciting and too bad at the same time. I've seen the practice exams, and they don't go into this, so I know that it's not being asked. I have temperature probes, and we can plug it into that really cool calculator, and you can actually do the experiments, but what's the point? You're one of us, yeah. Who cares? You and Spencer are going to be visiting the counselor soon. You're playing with guns, and you want to kill people. For calculus. It's only for science. Okay, anyways. There you go.